Okay, so we're going to get started now. So I'm going to present with my iPad here, and okay, so that's it. So I'm going to cover the questions, model questions of like week 3, but from previous year's assignment, not this year's. Okay, so these are going to be similar questions, but not the same question. So you can get the ideas of, and so these are the questions that we're going to solve now. Uh, Welcome, Costa. We just got started. Okay, and so hope you can see the screen. Is the Are the things visible? Can anybody unmute and say that? Are you able to see? Just a confirmation. Are you able to see the presentation? Okay. Yes, no would be desirable. Is it audible as well? Okay. Okay, I had muted my mic. I'm sorry. So, so I'm going to start again what I was saying. So, so is it audible now? Is it audible? Hello, anybody? Okay.
Yes, sir, it is audible.
Yes. So as I was explaining. So this is going to be week 3, and this is going to be of the previous year's assignment questions. These are going to be sample questions for you, so that you can solve this week's the present assignment week 3. Okay, so these are the questions that you can see. I hope it is visible, and so we're getting started now. Okay. Uh, so team is developing a neural network for agroscan. So an AI model used to classify crop conditions into 3 categories. So why we have are why that we has 3 values. So say y1, y2, y3. Okay. Now healthy, pest infected, and nutrient deficient. Okay, 3 categories, and you can understand as this is a classification problem. So our so many people have joined just suddenly. So what we are seeing is these are sample questions from previous years for a practice, and I was going through these questions, and so the first question is a classification problem, as I have explained, as there are 3 classes here. Okay, and there are 4 numerical features. Okay, so this is the output we have. The x we have are x1, x2, x3, x4. Okay, as you can see in the diagram as well, all normalized between 0 and 1. So these are normalized. The values of the features are normalized as well. These features are fed into a feed-forward neural network. uh, okay, so this is a feed-forward neural network. The architecture consists of an input layer with 4 neurons. Quite obvious, because there are 4 input features, so there has to be 4 input neuron, and the last layer would also be 3, because number of outputs are 3. Okay, middle layer has to be defined, which is defined as 3, as you can see, the hidden layer. Okay, the network uses cross entropy loss, very easy to understand. So what is a cross entropy loss? So summation of I equals to 1 to let's say this is k. Okay, k equals to 1 to number of classes. Okay, let's say, so in this case it is 3. So what is it? Cross entropy is yk. Okay, yk log of yk cap. So what do you understand from this? This is a cross entropy loss. What does it mean? is the this is the original class labels. Okay, what is the probable output? So maybe like 0 1 0 1 0 0, like that. What is the answer? I don't know. Okay, but it is given in the data set. Okay, but it is going to be like this. Okay, one is out of 3, one is 1 and rest are 0, and this is the probability. Okay, okay, so this is like and specifically this softmax probability. Let me come to that. So suppose this is like 0 0.95, 0 0.05, 0 0.05, like that. Okay, this will sum to 1. Okay, this is the probability distribution, the model outputs, that this is the real probability distribution. Okay, and this is our loss function. Okay, and in this case something to note is that at in our data set only one of these classes will be 1, others will be 0, right? And also a minus is there. Okay, it is just it is like you have to minimize this loss. Okay, so for that a minus is there. Okay, because usually we minimize. Okay, and one of this is 1. Okay, and the rest are 0, so this simplifies to uh, the class which is 1. Okay, log of y c cap, right? Because others are 0, so this is the structure we get. Okay, this we have to minimize. Okay, acha, this is 1. Okay, so what we get, minus log c. Okay, this is negative log likelihood. We have to minimize the negative log likelihood or maximize the log likelihood. Okay, of the occurrence of the true class. Okay, this is our structure for now. Okay, and so let us understand the network now. Okay, now you have to understand, this is done in the class as well, but let me still explain. Okay, so these are first of all, this will become small. So these are connected. Okay, so how are these connected? So each output here, so I'll do it like the class only. So this is like layer 1, this is layer 0, and this is layer 2. Okay, or the final layer. Okay, okay, now what we have is one the so first thing we have so they show it like this in the lectures as well, which is very convenient as well. Okay, so what it means is that so first the output here from the previous layer is h1, let's say, or what was the notation they used? H1 is fine. Okay, and the activation in this layer is G, let's say G. Okay, so what we'll have that this is the notation used there. So let me just check the notes once. Okay, check the notation so that we follow that notation, leading to no confusion. Okay, I think you can get the notation here. So So let's see the notation from here. Hope you can see. uh, so these are the inputs, as you can see, and this is the weight matrix relating to the first hidden layer. Okay, and here what we have is that these are the A1 and H1 in each layer, as you can see. Then there are A2 and H2. Finally, for the last layer, there is uh, A3 and HL. Okay, for the last layer. Okay, and so this is what we have. Okay, and so how AI is defined? So it is defined like this. Okay, so we'll take it from here. Okay, and so let me also define it here. Let me take another slide here. Let's do the drawing again. Smaller size though. X1, X2, X3, X4. Okay. Now, now what we have here is A1, A1, H1, A2, H2, like that. Okay. Now they have defined, as you can see in this, they have defined AI equals to, so AI, any I, okay, equals to BI plus WI HI minus 1. Okay, and each of these are function of X actually. Okay, but we don't need to write it in the function of X form. So this is the like linear function, you can say. So what you have from the previous layer, you're getting HI minus 1. Okay, you're multiplying with the weight matrix here. Okay, adding the bias term. Okay, then getting the new activation, new like values for the next layer. Okay, so now what we do, the AI values are then put into activation function is passed through it to get the new HI. Okay, this is the flow of the information, you can understand. Okay, so let us first understand what are the dimensions of these things. Okay, then it will be easier for us to go through the problem. Okay, I hope everyone is able to hear what I'm saying. Any confusion, any doubt?
Yes, sir.
Clear, right? You're able to understand everything I've told
Yes, sir.
till date?
Yes, sir.
Okay. Okay. So continuing, what we have. So these are the two important lines we have here. Okay. How the this is called the forward propagation. Okay. So let me just write it for this. Only three layers, so it is not very hard to write. Okay. So first what we do, we make a vector of the x features. So x1, x2, x3, x4. So what is the dimension of it? R4, right? Easy to see. Now what we are having, so x you can say is like h0. This is like the x is our like so you can understand h0 is like to fit in the equation. In equation there is no h, there is no x, right? So x is practically our h0. So what we're going to do now, there is a weight matrix W1 here, right? So how are you going to define that is the question. Okay. Now something to understand here is that uh, so there is also bias term here. Okay, which is not I have not given here. This is a bias term. Okay, b0, let's say. Here also, acha, bias term is taken with respect to the first layer. Okay, let me just correct this one. Okay, so bias term is here. This is B1 for writing the equation of the this first layer. Okay, I hope you don't get confused. This is B2, okay, for the second layer, the output layer. Okay, right. Now the bias term is also there, and okay, so we have to see here that for writing each equation here, suppose so this term, let's say, so this first neuron in the first layer. Okay, so this term, the a term, a a1, let's say a1. Okay, how we will have is like there are like connections from this, 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 and this, and one bias term, right? So bias I've written is a vector, actually it's not a scalar, but for this case I will have a scalar. Okay, let me show you. So this is a1, but the first term of it. Okay, so let me just check here. Okay, I'm going to use the same notation to avoid confusion. Okay, so it is a11, the first term is written as a11, so we're going to use that only. Okay, a11. So and I would like to write a11, so it's not very hard to write as well. So what is it's going to be? So what the weight value multiplied with x1. So how do I write this weight value? Let's see again. I'm going to follow the same notation to avoid any confusion. Okay, so here we have three term, as you can see, w111. So what does it mean? For the first layer, okay, we are writing for the first layer. So the first index represents the which layer we are at. Okay, now the second one corresponds to for which, so in which, let me see. So the multiplication I can understand from the multiplication actually. Yeah, so okay, so what we are having, this weight has to be represented in this way, in this fashion, that this is w1 for the first layer. So this is the first layer, as you can see. This is the first layer. Okay, this is the zeroth layer, then one layer, then two layer. Okay, this is what we're having. Okay, understood. Now so this is this one for the first layer. Then we have another for denoting the first neuron, first neuron of the first layer. Okay, so this one represents the which neuron in that layer. Okay, so first neuron. Okay, and now we will have one another subscript for the x that it is getting multiplied to, the weight for which it is. Okay, that is another one. Okay, understood. Now another one is w1 for the first neuron only we're doing. Okay, and what the x is changing, so x2, then w113 x3 plus w114 x4, right? These are added, then we have the bias term, right? How do you write the bias term here? So let's understand that one now. So bias term, it will be dependent on which layer it is. Okay, and which for which neuron, right? So I think that will be it. Okay, so b11. Okay, now I will write this as b11. Okay, so this is the equation we have. Okay, you can see that, and we can write this as, so the A11 of the first neuron of the first layer. Okay. Okay. Now I can pass this through the activation function G. Okay. G A11, this will give us H11. Okay, understood. Also you can write this X values as H. Okay, so how will I write now? Let me just show you that again. Little bit notation, that part is difficult here, but otherwise it's not difficult. Just the notation you have to handle. Let me do the drawing again. Okay, there are 4, 3, 3. Okay, now what we're having, I had written this equation with X, but I want to write in H because H is the common thing. Okay, because X is only in the first layer, but after that H only. X can also be represented H0. Okay, so I would like to write it that way. Okay, so so let's see the notation that was given. Okay, first let me write this one only. Maybe I can take a screenshot. Okay, now I take the screenshot. I paste the screenshot. Okay, are you able to see clearly what I'm writing? We're setting the notations and writing the equations. Will be able to understand what the dimensions of this vectors and matrices are going to be. Okay, so have some patience. Okay, so one thing we're going to do is now write the X in the form of H. Okay, so that also we'll get from the lecture ones. Okay, so what they're doing, as you can see, first in this index here denotes which layer it is. Okay, so X are all in 0th layer, and the next one is which number neuron. Okay, first neuron, second neuron, third neuron in that layer. Okay, so if it is in layer 1, this 0 will become 1, and then like that. Okay, so we're going to do that. Okay, now so I can write this as A 11 equals to, okay, W111 H01 W112 H02 plus W113 H03 plus W114 H04 plus B11. Okay, then H11 is equals to GA11. Okay, this is what we have, and understood. Okay, so what is my intention here? We have to understand what actually I'm trying to achieve writing this. Okay, I need to find the W matrix that is involved here. So we have understood that H0 is of dimension R4. Here the H will be of dimension R3. Similarly, right? Similarly, what we'll have, A is also of the dimension H1 A1. Okay, there is no A here. Okay, actually there is A here. Okay, A0 is dimension R4. This is R3, and similarly we'll have H2 of dimension R3, H A2 of dimension R3. Okay, clear, right? This is what we have, but we need the dimension of W1 and W2 as well, which are matrices. Okay, but let us see how is it a matrix, what is the dimension of that matrix. Okay, I hope you're able to follow. I'm doing it very methodically, easily. Anybody has any doubt, got lost somewhere? Any clarification required? Then I will continue after that. Good strength today. Okay. So I hope it is clear. Then I will continue. Okay. And so let us understand. So this is, as you can see, this can be written as a dot product form. Okay. So how can I write it? This a11 I can write as dot product of this w vector and h vector. So how do I write that? Okay. So this I can easily write as w, ready, w. So this is going to be transform like this. Okay. H0, yes. But what are the index of w? This is what we have to see. Okay. So this is for the first, okay, first layer. Okay, so we need that. And then what we'll have is also another thing we're going to have is the for the first atom, right, for first neuron. Okay, so one another. And so we can write it like this, right? And the rest is a, okay, so how will I write it? W11, as you can see, I can write as W111, W112, W113, W114. Agreed? Right? So I've written it like this plus B11. Agreed? And now H11, H11 is equals to G of A11. Clear, right? This is what we have. Okay. Now W11 is a vector, right? And it is a vector in which we have the varying dimension, the last dimension, it is varying, which represents what? Which represents the which previous layer neuron it is a weight of. Okay, I mean, like, these weights are actually varying this varying the importance of this age of the previous layer. Okay, if it is high, then this 801 has a higher importance. Okay, so like that you can understand. Okay, so this is what it is doing, and this is a vector of, and what is the dimension of it? Okay, so this will have dimension of r4, right? Easy to understand. Okay, this we are having. Okay, clear, right? Now another thing, so this is clear, right? And so we go to the next slide. Okay, so what now we can do is, like, for like A11 and H11 we have written, right? These two we have written. We can write it for A1 to H1 2, right? We're going to do that now. Ready? So now what we're going to do, so we know that A11 and subsequently H11. How can I write that? A11 is equals to W11 transpose multiplied H01. In doubt? H0. Okay. Plus B11. Okay. This G is A11. Right? This is what we're having. Okay. We can now write the other expressions. Okay. So what other I mean? This is the first layer, so we're still at first layer, but the second neuron now. Okay, is going to be W12 transpose H0 again. Okay, plus B12. Okay, now you have to understand this B11 is a scalar. Okay, you understand this? So this is a scalar. This multiplication is also scalar. A11 is also a scalar. Okay, and this is also a scalar. H11 is also a scalar. Can you understand this? Anybody has any doubt that who thinks that this should not be a scalar? Any doubt? These after this multiplication, this dot product, okay, this becomes a scalar. So these every quantity is a scalar, okay. After this dot product, this is also a scalar, okay. I think clear, right? Right. Now I can write this is H12 is equals to GA12. Clear? Next, what we're having is A13. We have three neurons, okay? So they are going to be three expression. W13 transpose H0 plus B13 H13 is equals to GA13. Clear, right? This one is clear. Okay. So, any doubt?
Two sides clear.
Clear, okay. So this is what we are able to write, and here you can see this is one vector of dimension 4, R4. This is W12 is another vector of dimension R4. This is another vector of dimension R4. Okay. So we now write W1, the matrix. How do you write it? We write the transpose of these as it is. And this is what we call W1. This is the W1 matrix. Okay. Anybody has any doubt? I'll also expand this transpose and show how it looks. Okay. But up to this, it is clear. So now I expand this. Okay. So from the previous one, you can see this is going to be W114, 111, W112, W113, W114, like that. Then with W121, W122, like that. Okay. It's going to be like this. Okay. Okay. So now you can understand there are three rows. Okay, as you can see, and each having element 4 elements. Okay, so this is 3 cross 4. Understood? Now you have to understand this W1. So I first defined W1. Any doubt up to this? Okay, the first question actually asks the dimension. We have got the dimension. Okay. Okay. So let's go to that. Okay. Let's go to the question. Okay. बात भी नहीं कर सकती मैं कहती है जैसे लगा बात कर तुम काट दो या शिका दो दो ना तो ऐसे कर कुछ ऐसा क्या क्या विशेष हो गया तुम्हें मैं 3 दिन से बात कर रही हूँ विशेष ओ भाई नमो बात सुन नमो बात सुन 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 नहीं नहीं पता है नमो बात सुन मेरे को कितना कॉन्सेंट्रेट है हाँ हाँ
Prakriti ma'am.
Unable to actually.
Prakriti
Unable
ma'am,
to.
can you
ये
please
आगे
mute?
पेपर्स और ये काउंट होते हैं
I'm unable to unmute actually. I don't know why.
मेहनत करती है तेरी मम्मी पेट्रोल नहीं लगाती और तो और तुझे क्या पता है ऐसे तेरी मम्मी सारे एफर्ट्स इसलिए डाल रही है अगर कल को गुड़गांव भी जाना
Sorry, I had to remove actually. I could not mute actually. Okay. So so what we're having, this is a question we're having. Okay, and hope you're able to see. Okay, and so The network uses cross entropy loss, that is what we are using as well. All bias terms are 0, so that is new information. And weight matrix is a W1, okay, and W2, okay. So this is what is the correct dimension of the W2 in this setup, that is what they ask, okay. So let us see that. So they need the dimension of W2, so it is going to be very similar actually. So how do I show it? First need to make it small. Okay, you're able to see now. So W1 we have got, it is a of dimension 3 cross 4, okay, clear, right? So let me again draw the neural network. X1 X2, I'm not writing it again, the X1 X2 X3 X4, okay, then this one, then this one, okay. This is what we are having. The weight matrix here is W1 of dimension we have seen is 3 cross 4. We've got this one, clear, right? Now how did you get this one? So the row in the weight matrix denotes the number of neurons in the layer for which we are calculating the weight matrix. So let us understand. W1 is of dimension 3 cross 4, where 3 comes from this layer. Okay, how many neurons are in the layer for which we are calculating the weight? Okay, and the 4 comes from the previous layer. How many neurons are there in the previous layer? Okay, so this is 3 cross 4 W1. So we have to do it similarly from W2. Okay, so W2, what we are going to do now? W2, it is going to be R. Okay, then the first term is number of neurons in the layer for which we are calculating, which is this layer. There are 3. Okay, and then the previous one, this is also 3, so this is going to be 3 cross 3, right? Yes, so it is going to be a matrix of size 3 cross 3. So let us mark the answer here. Okay, so we have done it, a lot of hard work to get to the answer, okay, but we have understood it very well, right? So this is what we are having, right? I just want to clear everything before we proceed through the other questions, okay. So we've got the weight matrix, okay, and we know how to write the weight matrix, okay, right? And so this is going to be this, okay, transpose of this, okay. Okay, so another thing we're going to write now is the bias term, okay, as a vector, okay. So for all the layers, it is going to be B. So as you can see here, it is going to be B11, B12, and B13 as a vector, okay. So also you can write A1 as a vector, right? What is it? A11, A12, A13. Clear? Absolutely. So there are 3 things. This is W1, this is B1, and this is A1. Clear? Clear, right? Let's add another slide. Okay. Now what I can write now is this A1 is equals to, so I'm actually trying to condense the 3 equations that I have written here into one single equation. So the 3 equations are scalar equations, right? All the terms are scalar except the, so after this dot product is also scalar, so everything is scalar, I agree, right? I want to write it in the vectorized form so that each element is actually a vector, okay? So A1 is a vector, there is no doubt. So A1 is equals to, I can write this as W times multiplied by x terms, okay? These are the H0 plus B1. I can write it like this, any doubt? No doubt, right? So let us just check the lecture notes if they have used a different convention or something to avoid any confusion. No, they have used the same convention, so we'll have no problem. Okay. Sometimes in some textbook, what you will have, this W1 is written as W1 transpose. So what that means is that they have actually defined it differently. The calculation everything is same. They have defined it differently. If you write it transpose, so there we have got, you have, remember we have got three. So here we have got the dimension 3 cross 4, as you can see. So in that case, the dimension will be actually 4 cross 3. So what it means is that they have defined it differently. What it means is W1 they will define as W11, W12 and W13, not the transpose one. Okay. So it is only a definition. Some books you'll have it differently. Okay. So just to be clear, okay, so it's just the definition of how they define the matrix is different. Okay, it is a notation. Okay, because in matrix we have not actually done anything right till now. Okay, we have just known how to represent this, okay, in a matrix and vectors form. uh, so there has to be some like assumptions like how you want to represent. Okay, so this is the equation we've got. Okay, and now h1 is equals to ga1. So this is what the definition is, that the G activation is actually applied element wise to every term of the right. So this is another definition how the G has to be applied. Okay, because G is a scalar function, right? It cannot be applied to vector. So how they applied is they applied element wise. Okay, clear, right? Up to this clear. So these are the condensed equation, vectorized equation. Okay, so each a1 h1 has a dimension of r3, h0 has a dimension of r4, w1 has a dimension of 3 cross 4, right? b1 has a dimension of r3. This is also g is a scalar function. Okay, this is the activation function g. Okay, can be anything. Okay, any activation function. Okay, the focus is not on the activation function currently. Okay, so now we are going to write all the equations to reach to our result. Okay, the next slide is going to be on that. So we are doing it very methodically to avoid any confusion. The questions are going to be very easy after this. Okay, so what we have, we started with 80 here, right, which is the x values. Okay, what we do is we multiply w1 with 80, we add v1 to it. This is our a1, no doubt. h1 I can write is at ga1, no doubt. Now I take h1, multiplied it with w2, then add b2, this results in a2. I put another activation, this, and become h2. Okay, so h2 is our actually final output as well. Okay, so as you can see, if I draw again, this h2 is actually the final output as well. So in the lecture as well, they have shown if it is the last layer, which is h2 is the last layer, so g is a output function. Okay, so in place of activation, they write it as output function. What does it mean? It means that you have to get a output according to the problem you have. Okay, you cannot apply any random activation function for non-linearity, because it is constrained in a way that you need a specific type of output. Okay, so that they replace the g with the output function. Okay, but otherwise this is the flow. Clear? So now what we are going to do is we are going to now understand what is the output function, how it is defined. Okay, so this is called forward propagation. Okay, so how we are moving forward to the result. This h2 you can write is at y cap. Okay, first we have, okay, so these are the y cap. So the y is our original result, okay, of the form 0 1 0 or 0 0 1, like that. Y cap is the estimated by the neural network. Okay, clear, right? And this is called the forward propagation. Next what we have is, next we get what this output function is going to be. Okay, so we see that suppose you have a single output. Suppose the dimension of y, this y, as I was talking, y or y cap, suppose the dimension is one dimensional, so it is a scalar. Okay, then you can use a softmax. Well, then you can use a sigmoid. Okay, sigmoid activation. So what is sigmoid activation? You can write sigmoid activation as, so this is the function. So you have to put the a2 here. Okay, or you can write, like, for every scalar of a2 you have to apply this function separately. So acha, so acha, if this is a sigmoid, okay, so a2 will be scalar actually. That is the given thing, because there is only one dimension it is. Okay, clear, anyone, any doubt, any? It, if it is a single output, okay, if the r1, okay, then a2 will be scalar, and then you can use a sigmoid activation. Okay, okay, if it is not, and if it is a classification problem but the output is multi output, then you have to use a softmax. Okay, so how do you write softmax? This is the question we have. Okay, so we write softmax as e to the power, then sum over e to the power. Okay, so what it is going to be, it is going to be e to the power, so minus is not there in this case, I think, and this is going to be, so you go to a2. Okay, a2 is our final. Okay, and this is like softmax probability, right? So this is calculated for every dimension actually. So what I want to you to see is that, suppose I calculate this for, so there are three dimensions of the output, right, in our example. So 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 a2 can be written as a21, a22, a23, right? So suppose I write for a21. Okay, this is going to be a21 and a2 I from 1 to 3. Clear? This is I. Understood? So so for every one of them, so a2 2 can be written as like this. Okay, just a minute. So a22 here can be written as e to the power a22. Acha, this is a na, so this is going to be h actually. Okay, any doubt? So this way you can get the values of each of these. Okay, then you have h21, h22, h23, so you can have the function vector h2. Okay, clear? So this is a full forward pass, every understanding. So I think we can solve the first question now completely. So which of the following loss activation combination are correctly used in agroscan? So the last one has to be softmax, right? So there has to be softmax in the answer, that's for sure. Achha, softmax activation has to be there at the last, okay? And then cross entropy loss, okay? So softmax and cross entropy. Clear? Compute the pre-activation values for the hidden layer for the input. This x is input and w is given, okay? So this is, you can say 3 cross 4, right? So it is called okay. So pre-activation and the bias values are 0, okay? So let's go to our equation. We had already written this one. So how do I write this? This was our thing, right? So they say this bias is 0. Every one of them are 0. So this is so what is the A1 they require, okay? Okay, because they say pre-activation. Before we apply the activation, what is the value we get? Is W1 times 80. So let's write W1. They have given a matrix for it, okay? And X values are also given. So the X values are 0 0.2, 0 0.6, 0 0.1 and 0 0.5. Yes. 0 0.2, I forgot. 0 0.6, 0 0.1. 0 0.6, 0 0.1, 0 0.5. Done. Next, the matrices are 1 0 1 1, 1 0 1 1, then 0 1 0 0, 0 1 0 0, 0 1 1 0. Okay. Next, what you have 1 minus 1 1 0 1, minus 1 1 0 1. Done. Just check if it correct, right? Okay. So this is what we have. Just a multiplication. So 0 0.2 plus 0 0.1, 0 0.3, 0 0.3 plus 0 0.5 is 0 0.8. The first is 0 0.8. Then what we have 0 0.7. Can you do this calculation easily? 0 0.4, 0 0.9. Can you do this easily? Because I did it. I did not write the step here. Can you do this or I should show you? Clear, right? Clear. 0.8. What was the answer? 0.8, 0.7, 0.9. Okay. Done. So you've done it very methodically, the first question. Okay. Let's see two other questions. So there are further questions on this actually. Okay. Now the question is, in the agroscan model, after performing the forward pass, so they have done the forward pass, okay? The pre-activation values at the output layer. So they're what they're calling is the pre-activation value at the output layer. So what it means is A21, A22 and A23, which is the vector A2. 2. Okay, what it is, so they have given it, they have given these values as 0.960 minus 0.27, 1.19. Okay, based on the computed probabilities, what class. Okay, so what we have to do is now apply the softmax. Okay, uh, so that is a question, the top question. Okay, uh, but you can understand this one, that softmax is like, just let's understand. So e to the power a to 1 by summation I equals to 1 to 3 e to the power a to I, right? For 1, if it is like the next one, it will be e to the power a to 2, but the base remains the same, right? Simple enough. Okay, so when you're comparing, we don't need to guess this one. We're actually comparing, right? We're not actually calculating which has the maximum probability. We actually need to compare. So base is not important, we can just ignore it. We need to compare e to the power a to 1, e to the power a to 2, e to the power a to 3. Clear? Now exponential is increasing function, right? If you remove e, it doesn't matter, the trend of a to 1, a to 2, a to 3 is enough. Okay, so take log. Okay, so what we get, a to 1, a to 2, a to 3, whichever is the bigger one has the highest probability of occurrence. Any doubt? No doubt, right? So this one has the highest value, a to 3 has the highest value. So which class has the highest occurrence of highest chance of occurrence is class 3. So what is the class 3? Let's see. Nutrient deficient. Okay, so answer will be nutrient deficient. Okay, done. So no calculation to be done. Okay, and just compare easily. No doubt. So let's go to the next question. In a classification tab, the true label is pest infected. Okay, so true label is this. So the vector we have is this one, and the predicted probability for class pest infected is, so predicted probability is 0.55. Use the cross entropy loss, cross entropy function, compute the loss. So we need the loss. Okay, so what is going to be negative log of 0.55, right? Hmm. This is what we have. This has to be done. Okay, suppose it is like base 10. Okay, so it is going to be, suppose it's base 10, so it is divided by 2, log 55 base 10, something like this. Okay, minus is also there, so 2 by, I think, acha, so I think this is it, right? Log, I think they're ignoring the minus. I think how do you want to say it actually, is the log of 55 base 10 by 2. So let me just see from Google what is the value. Log 55 base 10, 1.74, right? So 1.74 divided by 2, 0.87. Did not get the right one, I think. Mm, getting 0.87. Anybody has any idea if I'm doing wrong? Acha, I think they have not. Acha. Oh. Okay. I think in this problems they take at the base 2, I think, or base C. I took base 10 and I think it went wrong. Let's see what is the answer, okay? So I will try every base until we get the right answer, okay? Let's try base E. Oh, okay. Correct, okay. So in this problem, they are taking base E, okay? So natural logarithm they have written somewhere? No. So they have not written, but I think we are supposed to take base E. So I'm getting the answer with the base E actually, but not with and the negative is negative will also be there, okay? Minus log of base E 0.55, okay? Okay, this is the thing. Thank you, Jomi Susan, for help. Given softmax, what is the predicted class in the agroscan model? So this is the softmax output they have given. What is the predicted class? So with one with the maximum softmax probability, right? So answer will be best infested, right? Simple enough, right? How many learnable parameters are there in the above neural network in total? So they're asking for how many learnable parameters, okay? So we'll go back to our assessment, how we have done W1, B1, those things, and we'll be able to clearly see the answer. So we are here, okay? So this is 0, so there are no parameters here. Clear? H1s are no parameters, they are not already known, right? These are known quantities from the data set. A1, H1, A2, H2, these are calculated from the data, okay? This activation functions have no parameter, they take this A1 and then calculate, okay? So only parameters that we'll find here is in W1 and W2. What is the dimension of this 3 cross 4? What is the dimension of this 3 cross 3? 4 into 3 is 12. 3 cross 3 into 3 is 9. Summing up 21. Any doubt? See very clearly. First, we had to work so hard to understand the problem, right? But after that, it is too easy, right? Very easy, right? Too easy, actually. Once you understand the dimensions H1, W2, W1, too easy, actually. There's nothing in the problem, actually. 21, okay? Any doubt? No doubt, right? So what we're going to do now, more questions. So the hidden layer uses tan hyperbolic instead of sigmoid. Okay, what would change? So the G, as you had seen previously, is tan hyperbolic, not sigmoid. Okay, what would change? Activation outputs could be negative. Okay, let's see. Okay, so what is sigmoid? Like this. The output can also only be 0 from 0 to 1. Tan hyperbolic. The output can be from -1 to 1. Clear? Now, what we are having, so this is the situation we are in. Okay, now this activations G, as you would remember, was applied element wise to the G was applied to element wise of each A1 to get H1. Correct? Now A1 can be negative, positive, anything, right? It's a vector first of all. Its element can be negative, right? Why? Because X can be negatives, okay? And the weight matrix, weight values can also be negative. So product can be negative, right? So the A1 element can be negative, okay? Now even if you put a negative element to this, the output of sigmoid will always be positive, okay? Greater than 0, right? And in the case of tan hyperbolic, it can be negative, okay? So activation outputs could be negative, okay? This is a simple answer. Pre-activation cannot change. Our output layer would not be invalid in any way. Number of parameters would increase. Parameters are not dependent on the activation function. The parameters are dependent on the W and B. Only those two. Okay, don't depend on activation function. Activation function has no parameter. Which of the following can lead to higher cross entropy loss during training? So the loss they're talking about. Okay, predicting low probability for the true class. So that is correct. Okay, let's see the loss. What is it? The loss is minus log of y c cap. Okay, suppose c is the correct class. Okay, now we need a higher loss, so we need to higher this. Okay, okay, or you can write this as log of 1 over y c cap. Am I correct? Can I do like this? Yeah, you can. So if it is lower, then this will be higher, and log will is in. Okay, so log is an increasing function, right? Okay, so it does not change the property of higher or lower. Okay, so if y becomes lower, okay, if y decreases, this inverse increases. Log doesn't change, increase anything, so it does increase. The loss does increase in this case. Okay, predicting uniform probabilities for all classes. Okay, so if it is a uniform probability, okay, so what it would be, the number of classes are, suppose, k. Okay, so answer here will be, this one will be 1 by k, right? So this becomes log k. Okay, so this is a little strange one, honestly, because uniform you don't get the idea whether it is increasing or decreasing, because like suppose like there are 5 classes, 0 point okay, so the each probability equally is 0.2, right? Suppose before being it uniform, the probability was 0.1, so it can increase as well, but like but in which can they have written, okay, so it may be like it will decrease. Okay, so you have to take it like that. So predicting 1 for the correct class. Okay, so in the highest probability, so it can, so it will actually reduce it. Okay, So it will not be the class. Predicted class different from the true one. Okay. So you're predicting a different class from the true one. So that will certainly increase it because it is deterministically zero. It is all like close to zero. So it will be very large. Okay. So okay. Any doubt? No doubt, right? Next, which of the following are always true for softmax output? Softmax output is a probability distribution, right? So it has to be always from 0 to 1. Output lies in 0 and 1, correct? Output sums to 1 as well because it's probability distribution. Softmax is invariant to the order of inputs. Something to see, okay? So if the order of inputs change, suppose so softmax what we have is, suppose the input are x1, let's not write x1, suppose the input are a1, a2, a3. Cha. It is not invariant, right? Simple enough. Because why? Because when you're putting this e to the power a1, base we don't care about because it is only normalization. E to the power a2, e to the power a3, right? So the output here, this is the input, okay? This is the output, okay? So output does depend on it, right? Because like if you have right, it depends on the input, right? Here, like this, okay? So it is not invariant to the input, okay? And order, if you change the order, the of course the vector of, so this vector will change, right? If this goes up, okay? So okay, let me just give you an example, okay? Suppose suppose did you get this one? I don't want to get into it actually. Clear? Anybody? Doubt? Understood? Softmax is sensitive to relative magnitude of logits, so it is correct, okay? Suppose so what you're having, uh, let's see, relative magnitude of logits, okay? Suppose x, 2x and 3x, these are the values, okay? And if you make it double, right, 2x1, 2x and 4x, 6x, will the softmax change? Okay, it will not change. Why? So let's see. So you calculate it like this, okay? And so then what you do, you normalize actually, okay? So it will remain the same. Let me show you, okay? So e to the power x and sum of these, okay? So e to the power x I'll take common, okay? Can I take common? I can. So e to the power x, this will be 1, e to the power x, e to the power 2x, right? This is what we have, and this can change, e to the power x or e to the power 2x, e to the power 3x, like that. Suppose now it has becomes twice, okay? So I will take common e to the power 2x, I will be able to take that. This will be 1 e to the power x plus e to the power 2x. So now the upper parts are also twice, e to the power 2x, e to the power 4x, e to the power 6x. You see, it is the same thing. So it depends on the relative magnitude, not on the absolute magnitude, okay? Relatively, they are still the same, so the softmax scores remains the same. Any doubt? Because it is on the concept that the probability should add up to 1, okay? So if you increase the, if you keep it relatively same, okay, so it will still add up to 1. To make it add up to 1, the softmax probability will be same, okay? This is how it is, okay? And now the next questions. Okay, any doubt? No doubt, right? Let's continue. Another neural network, lot of questions. So there are a lot of questions actually. Okay, so let me just take a break, okay, of 5 minutes, and then we'll join back. Okay, I'm still in the call, but like I'll be away from the room. After 5 minutes, I will join. Okay, so I'm back. I think I'm early. Before starting, let me take the screenshot and those things. We'll not have time to finish all the questions, I think, but let's see. Should we get started again? Any feedback? Anything want to say? Are you able to understand before we start again? So you can code this out as well, okay? Uh, this is a back propagation algorithm. It is quite valuable to implement actually. You just take a simple problem, let's say uh, image classification problem. So you can pick the problem from Kaggle actually, and you can write the code in Python. Okay, so how do I do it? This is a classical assignment in any ML course. So so I go to Kaggle. Acha, you cannot see it, right? So what I'll do now, I will present. Okay, I will uh, I will present from here. Okay, are you able to see now? Are you able to see? You're able to see, right? I'm presenting from a laptop now. So I'm writing a Kaggle uh, image classification dataset or like that. Okay. So from this you can get the dataset, right? Acha, acha. Intel image classification. Let's say this one. Very slow. Mm, it is very slow. Will it work out? So this is also, so I'm not able to open it, so I could show you, but there are many classification data sets. So we are actually discussing classification only in different classes, softmax, probability, those things. Okay, so so it will be like that only. So as you can see from this only, that there are 25,000 images of size 150 cross 150 distributed under 6 categories. So there's 6 categories, 6 classes. Okay, so with image what you have, okay, so now here we are having features, right? So image, what are the features actually? So what you have to do in case of image, okay, you have to flatten the image. Okay, so you have to the row, okay, the first row becomes a vector, then the second row another vector joins after this, okay. So you have to flatten this image into a vector, so it will be a vector of dimension 150 multiplied 150, whatever that is. So it is 2225 right? So that is the dimension of the vector. Clear? You have to flatten that, and so each pixel is actually feature here, you understand? And then it is the same problem, okay. So you write the forward pass, but don't use any library pytorch or tensorflow. You write the forward pass we have already done, okay. And then you write the code for backward pass, okay. It is in the classroom as well, what are the equations you have to write, okay. You have to write in the vector form, otherwise it will be too slow, okay. And then it is done, okay. So you have to define. So what you can have is like so the so as the number of images are large, so you can have a larger neural network. So if there's like the first layer is also huge, of course, then you can have suppose 3 hidden layers, okay, each of dimension like let's say 5000 in the first hidden layer, then 2000, then 1000, and then the last six six neurons, okay, at the last layer, because you need 6 as the softmax output, right? Six probabilities, okay. Clear? So you can solve a problem like this, okay. It is failing to open here. So what I will do, I will share the link, okay. You can try, okay, and maybe we can discuss in the next class, okay. Now this is it, okay. Now what you have, so if it might be that it may be too slow without GPUs, okay. The GPUs are also available in Kaggle, okay, so you can use that, okay. I could not show you. Let me see if it's possible to. Kaggle. What did I open? Is this? So how do I? So if I switch the internet, will the connection break? Let me try. Okay, so can you see? Can you hear me? Can anybody respond if they can hear me? Please. Okay, okay. So now with after switching the internet, I was able to log in to Kaggle, access Kaggle server. So these are the classes, okay, and so test train dataset, everything is done here. Can you write a code to do image classification with just Python and NumPy, okay. This can be your task. I can discuss it in the next class, okay. This will be a valuable thing to do, okay. Classical deep networks problem, right? You have a lot of data, and you can make a complicated architecture to solve it, okay. Okay, so let's move to our current problem that we have, okay. And I will again present from the my iPad, okay. And we'll solve the questions there, okay. So what was trying to do, present from here, no? Okay. I'm presenting from my tablet again. Are you able to see again? Okay, we're back again, and now this is a new question we have. So there are two hidden layers, so three weight matrices now, and let's see what the problem is. So there are five features, so five input nodes. Okay, neural network with two hidden layers. Okay, very easy to see. First four neurons with tan hyperbolic activation. So here they have G tan hyperbolic. Okay, so T H. Okay, hidden layers with sigmoid. So then there is sigmoid activation, and then there is linear activation, means a linear function. Okay, okay. So what they do now? So in case of linear activation, so in the case of linear activation, they they take another weight. Okay, and then a bias. Okay, a linear combination. Okay, now you have to see that in the last layer what we're having is a vector, right? And so what they do, they will have a simple one. Actually, let's see, let me explain. Okay, so the last will have, suppose, so this is a, so this will be, this, for this it will be a1, for this it will be a2, this is a3, right? Okay, so you have got a3, which is a scalar. Okay, and now to get h3, what you will do is you multiply it with w, some weight value, multiplied that. Okay, it's scalar multiplication. Okay, no problem, and add a bias. Let's write at 0. Okay, like that. Okay, easy. So this is what the linear activation means. Okay, I will see to that. Okay, so this is the standard problem we're having. Why is the output activation in leaf YL chosen to be linear? It is chosen linear so that it is unbounded in unbounded. Okay, so it can have any value. Okay, so it is a regression problem, done for a regression problem. Okay, so softmax is unsuitable for a regression problem. That is the easy answer. We need raw values and not probabilities, so that is also in regression, because sigmoid would squash the output range, so it will be okay. So all the above. Okay, what is the output of if w3 is this and activated value of the second hidden layer is this? Okay, so they have given w3 as this, so this is w3, and w3 will be a vector. Why? Okay, okay, so just a minute. So ready. Okay, so w3 is given, an activated value of second layer, so h2 is given. Okay, so we need to find this. Okay, so what we were doing back then, remember, it is w3 times h2 plus b. Bias is 0, I think, in this case as well. They have not written. Okay, I think they want to say that there is no activation here. Okay, and now w3 is 1 1 minus 1, so it is just, so in this case it is like 3 cross 1, right? 3 row. Am I correct or wrong? What was the thing or we had? Okay, so it was like, it is going to be 1 cross 3, right? Yeah. The dimension of w3 is 1 cross 3. It is a vector, so it is like this. Okay, you just need to multiply it. Okay, 0 0.73, 0 0.9, 0 0.91. So it is 0 0.73 plus 0 0.9 minus 0 0.91. Okay, so minus 0.01. Okay, and you subtract 0 0.72 is our answer. Done. Which loss function is most appropriate for this? Mean squared error regression problem. Okay, so more questions now. Given the number of neurons in the layer and bias is used in all layers, the number of learnable parameters. So this is the question we have. So what we had in the question, I had to remember. So this 4 5 first, 5 4 3 1. Okay, 5 4 3 1. 5 4 3 1. Okay, this is what we're having. So the weight matrix dimension is 4 cross 5, right? This is W1. W2 is 3 cross 4. Then is W3 1 cross 3. Any doubt? Clear, right? So here the B dimension is, the B1 dimension is, what is it? R, number of equations related to this. So R4, then it is R3, it's R1. No doubt, right? So number of parameters in this are 4 plus 3 plus 1. Weight matrix is 5 4 20, 4 3 12 and 3. So this is 32, 32 plus 3 35, 35 plus 1 is 36, 36 plus 4 is 40, 40 plus 3 is 43. Done? Clear? Done, right? Given output layer activation is linear and pre-activation value is 3.75, what will be the model's prediction in the... Okay, so they're actually not applying any activation, so answer will be the same. Okay, which of the following statement are true about the activation function used in leaf yield? Tan hyperbolic values are from -1 to 1, sigmoid from 0 to 1, linear activation has no bound, that's also correct. Sigmoid is centered around 0 than, more centered around 0 than tan hyperbolic, that is wrong. Okay, let's see. So what is so tan hyperbolic is like this, sigmoid is like this. Okay, so the center of the sigmoid is like not at 0. So center, how do you calculate center? You take the mean. Okay, so mean of all the values of, suppose you discretize. So what you do to understand this problem, let's say, so tan hyperbolic is e to the power x minus e to the power minus x by e to the power x plus e to the power x, like this, something like that. Okay, now what you need to do is integrate. Okay, or maybe this is like easy to see, don't need to do too much. Okay, tan hyperbolic is symmetric around 0. So for every positive value associated, suppose there is x1 here, there's so tan hyperbolic, let the function, let the tan hyperbolic function be f. Okay, you apply this, so there is another, always another one, minus x1, which is equals to negative of this. Okay, okay, so if you add those values somehow, it will always at center at 0. So tan hyperbolic is mode centered. Okay, given the input vector x and w1 this, what is the pre-activation vector? This is very easy, multiplication, you can do it, right? So I'm not going to do it again. Okay, you can do it. More questions. Okay, okay, so let's start again. Ready? So first question is unable to see. Let's see. So the first question is here, tan hyperbolic. So you can do that, right? As well. Tan hyperbolic, just you have to use the function. Tan hyperbolic, as far as I remember, is e to the power my x minus e to the power minus x by e to the power x plus e to the power minus x. Yes. So you have to use that function. You can use a calculator now. We will do that too much. Okay. So now let's go back. This is what we're having. Okay. Now the question is, the leaf field model were tested on 5 plant samples. This is the question we're currently on. The true and predicted crop yields are like this. Okay. What is the mean squared error? So it is very easy to calculate as well. Okay. Do I need to do this as well? It's easy, like I can do it orally as well, but orally it will no help. Okay, let's do it. Okay. So 3 minus 2.7 square, 4.5 minus 4.2. So these things, okay, like that, square. So let's see how much it is. Okay, so this is 0.3 square is 0.09. This is 0.09 again. Next what we're having is 0.25 next we're having is 0.25, next we're having is 0.09. Let's add this one, 27, 0.27 and 0.5, 0.77. This is squared value, and then we have to divide by the number of elements, which is 5. Okay, so let's multiply by 2, then divide by 10. Okay, 7 to 14, 7 to 14 and 18, and this will become 0.184. Sometimes they also divide by, I don't know, something like this. You can check, I don't think this is wrong. 14 and 14, it is 15, so this is 154. Okay, 0.154, so answer is this one. Okay, done. Which layers weight will receive gradient first during back propagation? Okay, so now we are getting to back propagation. Currently the questions are all forward propagation, right? So now what they're saying is that, so you have the structure like this: 5 first, then 3, and then 1. So first what you do, you calculate the loss. Okay, this is the loss function, and now you need to back propagate it. Okay, so what we are having currently, let's see. Let me take another slide. Okay, I will explain it as much as I can. Okay, ready? So now let me draw it again. Right, now this is H0. Here we will have A1 H1, here we will have A2 H2, then we will have H3. There is no activation after that. Okay, this is the structure. Okay, now let's understand the flow as well. Okay, so first we'll have H0. A1 is W1 A1 plus B1 A0. Okay, now H1 is G of A1, done. Then H2 is, okay, A2 is W2 A1 plus B1 B2, done. Then H2 is G of A2, then A3 is, acha, so this is A3 actually, and A3 is H3. Okay, that is how they have defined. Okay, A3 is equals to H3 is equals to W3 A2 plus B3. Any doubt? Any doubt here? No doubt. Okay, this is what we have. Okay, and so these are the forward pass equation. Okay, now so these are the parameters B3 W3 as we know. Okay, B2 W2 B1 W1. Okay, and we need to calculate the gradient update with respect to this parameters. Okay, so that we can write the gradient update equation. So what is the gradient update equation? Let me see. Okay, so this is our theta is theta t at theta t plus 1 minus this learning rate, and then divergence with respect to parameters theta t. Okay, of the loss function. Any doubt? This is the backpropagation algorithm. So we need the divergence with respect to this parameters so that we can calculate the, so that we can do the backpropagation with respect to each parameter. Okay, so this is what we are having. Okay, okay, correct, right? So now, so the loss is this, okay, and the first parameters that are exposed to the loss are B3 and W3, without any doubt, right? So, so del y cap by del W3 and del y cap by del B3. These are the first two we have to calculate, right? Clear, right? This was the question we are having here. Okay. Which layer's weight will receive the first gradient during backpropagation? The output layer is the answer, okay? Because they are the closest. The first derivative will be done for them. Then chain rule, okay? We're close to being done, okay? There were some questions left, okay? More importantly on backpropagation. We will for sure do these questions first or next week, okay? And then carry over for week 5 because these questions I think will be important. Or is it important? These are not important. Will this assignment question be available PDF? Oh yeah. I will share this slides. Okay. So in the form of PDF. Okay, you'll have that. Okay. They don't have any back propagation question. So that's very unfortunate actually. Okay. So we're stopping here now. Okay. Thank you very much.